It's not recording. Okay, there we go. I think it's recording now. Okay, so having said all that about the test, I'm going to go ahead and kind of get started on what we're doing today. We're looking at worksheet 6. By the way, the worksheet 6 will not be on your test on Wednesday. Also won't be on the AP test. But for instance, the last internet homework, there were a couple questions on it. Again, you could have chose not to do those. Remember, you only have to get 6 points out of the 14 points. So anyway, so that's what we're going to get started on today. Probably should tell you a little bit about this attendance thing. I know you've probably thinking, what the heck? It sounds a little draconian. Well, here's the problem. I have to somehow account for your attendance during all these e-learning days. And so, and I have to do it in such a way that it's fair for students who can't attend because, you know, maybe they have work or they have an internship or something like that. And so how to make it fair is that I'm going to have this SWIC, which isn't like the other SWICs we've been doing. It should be a really simple. It's not supposed to be a penalty. It's just like an attendance thing that you watch the video that I'm recording right now and that you can answer some of the pretty simple questions if you just watch the video. So it's not like you need to freak out that you have to get this done. I just want to make it so that there's a couple different ways that you can get your attendance, either by doing the whiteboards and sharing and coming here and then you're kind of done with it. Or if you weren't able to get through all the whiteboards for whatever reason, or if you weren't able to attend, that's all right. You can still get your attendance by doing this attendance SWIC, which will be super easy. It's not going to be a pain at all. Okay, so try not to freak out about it. Okay, having said all that, I need to give you some of the code for the attendance SWIC to access it. So everybody should write this down because you don't know until maybe at the end of this whether you'll have to do the SWIC or not. So the code's going to consist of 9 digits, and I'm going to give you those digits at different times. Before I give you the first 3 digits, what I'd like you to do is in the text chat, if you're here, if you could please type in your full name, your given name and your surname, okay? That's going to be another way that I'm taking attendance. I'm going to ask you to do that multiple times. So again, if everybody who's here right now could go ahead and type in the chat your full given name, your given name and your surname, full name. Okay, sorry about that. All right, so the first whiteboard we're going to look at is from worksheet 6, number 1. Usually when we did gravitational energy, we said that gravitational energy is equal to mgh, but unfortunately we can't use that anymore because now the gravitational force isn't constant. Near the surface of the Earth, it pretty much is constant. It's just mg. But as you move further and further away from an object, it becomes no longer constant, it becomes an inverse square relationship. So the first question is, well, how could we find the gravitational energy? So I think I'm just gonna try to pick a group at random. Let's see here. All right, this is slow opening.
If you want.
Okay. Okay, I'll click on Chaitanya's whiteboard if it'll let me. Oh, it says it's denied. All right, why is it denied? I was just looking at it a little bit ago, Chaitanya, so I don't know why it says it's denied. Oh my gosh, come on. There we go. I don't know why it said denied before. Okay, so it says, how could the gravitational energy storage be determined graphically? Yeah, you just find the area of it. So it's just simply going to be the area underneath this curve, which, you know, looks like it might be a little bit difficult to figure that out, but you can draw in triangles and rectangles to find the area, different sections to estimate. And so that's kind of what we're doing here. All right, so thank you very much. The next one, number 2 and 3. Let me pull that one up. Okay, 2 and 3 are looking for how much energy is stored when we go from 2 to 3 Earth radii. So 2 Earth radii is right down here. I don't know if you can, actually probably can't see my cursor. I don't know if you can or not. So we're talking right about here is 2 Earth radii, and 3 Earth radii is right about here. If it's possible, some of you, we're getting some other noises in the background from other people. If you've got headphones or if you've got earbuds, it'd really be helpful if you put those in and plug those into your computer. Okay, thanks. So we're trying to figure out what is the area stored, or what is the area underneath the graph between 2 and 3 Earth radii. Okay, so let's see if I can click on one of these other links here. Let's see, Gabe and Sydney's didn't work when I clicked on it, so maybe I should just paste it. Let's see if that'd be faster. Oops, I clicked on the wrong one, of course. Okay, so from 2 to 3 Earth radii, again, we're just finding the area underneath the curve. And I wonder if I could, sketch in here. Let me draw from 2 to 3 Earth radii. So from here to here, we're finding the area of this kind of trapezoid area. So you can break that up into a triangle and a rectangle kind of thing. So let's see, they did 6.37 times 10 to the negative 6th. Or wait a second, 6.37. Oh, okay, so 6.37 is the radius. So that's the kind of the width of this thing. And again, I'm still getting a lot of background noise. Like hearing some kids in the background. Don't know if you can close your door. If you could please put earbuds in so we're not picking up that extra noise, that would be great. And let's see here. Then multiply that by the 2 forces, then divided by 2. And they got an answer of, looks like 56 million or so joules. And then for number 3, again, kind of the same idea, and got around 27 million joules. Okay, thank you very much, Gabe. Okay, that's that one. I think I want to try something different. So hold on a second here. Stop share. Okay, so I've kind of shared with you, there is a green button at the bottom of your screen that says share. Is there somebody who'd like to share their whiteboard that they got it pulled up for number 4? Anybody that's pretty comfortable with calculus that would like to kind of talk us through how you would solve that one?
I could do that, I guess.
Okay, you want to try hitting the share green button at the bottom? And what that does is it lets us see your background on your computer, or lets us see your, yeah, perfect. So yeah, talk us through for number 4.
So for number 4, I tried to basically, the area equation for this graph would be the antiderivative of the graph,
Okay.
or of the original equation. So I didn't actually show the steps through it, but basically I combined all of the numbers in the equation that you could combine, and then over r squared. So that would reduce down to like r, basically, when you do the antiderivative of it.
Okay.
And then you have the constant of c, because when you derive numbers just sort of cancel out. So you have a C value that you don't know what it is, but that should
Right.
equal EG.
Perfect. So I do want to talk about that C constant, because the nice thing about that constant for physics, and in math it comes up a lot where you need that constant, but for us in physics, a lot of times for gravitational energy, we don't care about the energy at one location. We care about the difference in gravitational energy between two, so a change in energy. So what happens is that C value drops out. And so, in other words, we just have that first part. And I really want to talk about that number you have there. That number really is, and if you can maybe type it underneath it or something, it really is negative big G, big M, little m over R. That's really what that is. So negative big G, big M, little m, and then of course, just like you have there, over R, little r. So usually we use the equation EG is equal to mgh, but now whenever you have an inverse square relationship for the force, we have to use negative big G, big M, little m over R. Okay, nice. Okay, then number 5, you said, oh, okay, so explain how you got 0 for that there, Jack.
So as R would increase to like infinity, you could say because it's being divided, like some number is being divided by R, as R gets bigger, the other one's going to get smaller, but it will never really approach 0. But it like, if you were to hit infinity, technically it would be 0.
Okay, nice. I like that. So the only place that it would really ever be 0 would be at infinity, which of course you'll never be able to reach infinity, but at infinity, it would theoretically be 0. Good. And then number 6, you weren't really sure about that
Yeah,
one.
but I think I got it. It's basically if like when energy approaches 0, it'd be R equals infinity because like 0 is the reference level.
Right, that's exactly right. So you remember back when we were looking at like Tarzan swinging on a swing, or let's say we were talking about, remember I did the demo where we had this ball up to your nose for energy. We let it go, and then we were trying to see if it would come back and hit you in the face, and it doesn't, right? Well, that was conservation of energy stuff. We always said the bottom of that swing, we said that was the reference level. Why? Because it couldn't go any lower, so we set that to be EG equals 0. Well, now that doesn't make sense with this new equation, negative big G, big M, little m over R. It doesn't make sense to just put your reference level wherever. It makes sense only where that would actually be 0, which happens to be, as you said, at infinity. So from now on, for these types of problems, we're going to say that the natural reference level would be way out at infinity. That's where the gravitational energy would be 0. Perfect. Thank you very much for sharing. So now if you could unshare, perfect. Okay, so any questions on that, 4, 5, or 6? All right, okay. Before we go on, let me give you the other 3 digits. But before I do that, could you again, in the text, could you please put your full name again? So your given name, your surname. So if you go ahead and type those in.
I'm ready for the Joel. What was that? Joel?
Did you say the first 3 digits?
Yeah, I already gave you the first 3. Okay, now the next 3, and these are all lowercase again, just like the first ones were, is Z as in zebra, D as in dog, and the number 1, ZD1. All right, so now we need to look at the next problem, number 7, and this might have been a hard one. I don't know. So your hint here is conservation of energy. So again, does anybody want to share their whiteboard? It's kind of cool actually doing the share. Okay. Well, let me see if I can go ahead and pick somebody then. All right. Let's see. This is number 7. So I'm going to pick on Nathan's board, see if I can get that. Oh, I don't think am I sharing? I don't think I am sharing. Hold on a second here. Sorry, I need to share so you guys can see what I'm doing. Sorry. Okay. All right, so what we have to do for this is we have to do conservation of energy. And actually, I think this is Nathan's board, and I'm going to kind of draw on a little bit. Here's the Earth. Imagine we have a rocket ship. Let's see if I can draw a triangle. Imagine we have a rocket ship on the Earth, and it's taking off. And eventually, it's going to be really far away. We want it to escape Earth, so it's super far away. And you want to think about the energy of these two locations. At the first location, it's going to have two storages of energy. It's going to have EG, and it's going to have a kinetic energy, EK. At the last location, it can also have those two energies, but if we're saying it just barely gets there, its kinetic energy is actually going to go to 0. In other words, its speed is 0. Okay, so if it just barely is able to escape, so its speed 0, and so the kinetic energy is 0. Also, we're going to assume that it's infinitely far away, which means now the gravitational energy would also be equal to 0. So we would have to set these two energy equations equal to one another. So the initial energy equals this final energy. And so remember that the equation for gravitational energy is negative big G, big M, little m over R. And of course, the kinetic energy is 1/2 m, which is the little m for the rocket ship, times v squared. And this, of course, is equal to 0. We can move that gravitational energy storage to the other side, kind of like what Nathan did here, but unfortunately, it's not going to be r squared, it's just r after the integration. And so then we can solve it. So let's see, you got one here. Oh, we dropped off the r there, that's good. The m's canceled. And then you can plug in, take the square root, and yeah, I do agree with that answer. So it's around 11 kilometers per second. Any questions on that one? Okay. All right. Then let's see. Does anybody want to share the next one? The next one is number, actually, you know what? I want to jump around here because I want to make sure, I don't want to be on here too long. I want to make sure that we do 9, 10, and 11 because that kind of stuff you'll need to know. Well, for my test anyway, since the AP test isn't going to happen anymore. All right, so number 9, we're going to skip number 8 for now. We'll come back if we have time. Number 9, does somebody want to share that one?
I can.
Oh, who's that again? Oh, okay. All right, so let me unshare and then I'll have you, Gabe, go ahead and share. So at the bottom, there's a little green arrow for the share. Okay, and then you click that and then you just share your desk. There you go. And this is number 9. Okay, so why don't you walk us through what you're doing here?
So plugged in up here to mg equals gmm over r squared, and then the m's cancel out. So this is the equation you get. And then I plugged in, it's 1/10 of the Earth, so m over 10, and then 1/2 r squared, which that would actually be 1/4 r squared. And so you get, it would be 4, you get 1/10 on the top of the equation and then 1/4 on the bottom. So it'd be 4 over 10.
Okay, so stop right there because I agree all the way up to your second step there where it says 4/10 mr squared, where that mr squared is kind of like the same as the Earth, right? M mass of the Earth over radius of the Earth squared. So what I don't understand is how did you go from 4/10, which I totally agree with, to 10/4? I don't.
Well, because I got 4/10 on the right side of the equation, so I multiplied the inverse to the g to get it on the g side. I don't know.
Oh, okay. Now wait a second. Actually, I think you wanted to stop up above. So it's really going to be 4/10 of whatever it is here on Earth. So on Earth, it would be what value?
10.
10. And so 4/10 of 10 is
0.4.
it's actually 4. Yeah.
Or
So
4,
the answer is actually D. Does that make sense?
Yep.
Okay. So yeah, that's exactly right. Remember that the force of gravity increases with the mass. So if the mass went down, the force had to go down. But it actually is an inverse square relationship with the radius. So if the radius gets smaller, like it did here, that means the force is going to get bigger. So if the radius got smaller by a factor of 2, that means the force is going to be getting bigger by a factor of 4. So we have to combine these two. First of all, the force goes down by a factor of 10 because the mass went down by a factor of 10. But the force also goes up by a factor of 4 since the diameter, the radius, went down by a factor of 2. So that would be 4/10 of whatever it is here on Earth, which is 4. Okay, nice. Thanks for sharing. Appreciate it. So you can unshare now. Perfect. And then how about number 10? Does everybody want to share that one?
I don't have it done, but I could work through it.
Okay, that sounds good. Why don't you share that one?
Okay.
So at the bottom, you just click the share. Yep.
And oh, this is kind of trippy. I'm sorry.
That's all right.
Um, yeah, when we do the whiteboards in class, I'm usually wrong, so I just work through it in class
Okay.
anyways.
Okay, that's fine.
Here. Oh, it's 10?
Yeah, this is number 10. So for this one, Aiden, it says that we have some object with a weight W. But now we're going to take this object that has a weight W on Earth, and we're going to go to another planet with a radius R. Or it's going to be a radius of 4R. So remember, it's an inverse square relationship. So if the distance, the radius increases by 4, what's going to happen to the force? Does it go up or go down?
It's gonna go down.
Right, and it would go down by a factor of what? Since it's inverse square.
So it would. So
So
can you say that again?
it's inverse square, and you're right, it goes down. So if the radius goes up by a factor of 4, the force is going to go down by a factor of how much?
4.
Well, that's if it's just inverse. This is inverse
Oh, so
square.
it'd be 16.
16, right? So the answer has to be,
So A. Right.
well, that would be getting bigger by a factor of 16.
Sorry.
Yeah. So does that make sense?
Yeah.
Okay, so if you're setting up the equation, it's kind of like Gabe's problem there, that in this case, the mass didn't change, but what happened was the denominator increased by a factor of 16, so that means the weight goes down by a factor of 16. Okay?
So, okay.
All right, so if you can unshare. So now we have one more, number 11. Does somebody want to share that one? At the very bottom, Aiden, there's the green button, if you can click that and unshare. Or maybe you hit stop or something, stop share.
Okay.
There you go.
Sorry.
That's right.
This is new to me.
Yep. Okay, so let me pick another one then. Let me first share my screen. All right, so maybe let me check email. Maybe somebody sent me something, number 11. Okay, so Luke sent me something. Click on his. Okay, so this is Luke's. We go to this new planet that has twice the mass of Earth and twice the radius. So if you're thinking about this, the force is directly related to mass. So if it's twice as massive, then the force is going to go up by a factor 2. But it's also inversely squared related to the square of the radius. So if the radius gets bigger by a factor 2, the force is going to get smaller by a factor 4. So really it's going to be a factor of 2 force that the force changes by. So that's a half, and we got an answer of 250. So I totally agree with that. So here's the thing, some people are putting in numbers. I don't have a problem with it. It's not that it's wrong by putting in the numbers, but what's going to happen when you don't remember the numbers? Or what happens if I give you 2 planets that we don't know the mass or the numbers for? I give you planet X that has a mass of m, let's say, and a radius r, and I want you to compare that to planet Y that has a mass of 3m and a radius of 9r. Well, using numbers isn't going to help you too much. I mean, I suppose you can make up your numbers, but really what you're thinking of is, how is the force related to the mass? How's the force related to the distance? And that's how you figure out the answer here. It's just proportional stuff that you're doing. Okay, that's number 11. Any questions on 11? Okay, let's see if we can quickly get through number 8. But before we do that, could you please, again, put in your name, your full name, your given name, and your surname into the text chat. And let me give you the last 3 digits of the 9-digit code. It's the percent symbol, the number 5, and the number 3. Percent 53. That's the last 3 digits.
Mr. Lenfestey?
Yep.
I don't think I remember ever hearing the first 3 digits, if I'm honest.
Then you'd have to go back and look at the video. It's right when you put in your name the very first time.
Okay.
Okay, so let me go ahead and see if does anybody want to share a worksheet or problem number 8. Okay, so let me go ahead and just pick somebody then, and then I will talk about who has to, because not everybody's going to have to do this week, and even if you have to do this week, it's not a penalty really. It's not that hard. It won't take you that much time, so be thinking of it as a penalty. All right, so let's see. Oh, let's see if I can click on this one here. Okay, so for this one, for number 8, you had to do lots of different things. This was an actual AP problem for a few years ago. We had to find what the velocity was, and I think you just simply use D equals V bar T, and that's kind of what they did. I got 3.8 times 10 to the 6 meters for the radius, and I think that's what the groups got here, this group got here. For part B, you had to find the mass, and so I set the net force equal to the gravitational force, and I just rearranged it to solve for the mass of the planet, and I got a number of 6.64 times 10 to the 23rd, and I think that's what this group, actually they had a slightly different answer there, so I kind of agree with Sophie and Chloe here. Okay, so Wendy might want to kind of look over your calculation again. Okay, then part C, calculate the total mechanical energy. Now this is using that new equation for gravitational energy, so I'm not so sure how we did on this one because it might have been kind of tough. Especially what happens is sometimes students forget the negative sign for the gravitational energy. It's going to be negative G, big M, little m over R. Anyway, when you add that to the kinetic energy, I got an answer of 5.36 times 10 to the 9th. So I'm not sure if anybody was able to get that one. Oh yeah, right here. Wait, except we got a negative. I did not get a negative, I got a positive. Okay. Part D. If the global surveyor was to be placed in the lower circular orbit, would a new period be greater than or less than or the same, I guess? Or no, greater than or less than, and justify your answer. We kind of talked about this one. I had less than. I think everybody said less than. And my rationale, did I put my rationale? Oh, since the radius goes down, the speed goes up, and the distance goes down. So the speed goes up and the distance goes down, so the time would go down kinematically. And then finally, part E. Let's see. Part E, that might have been a tough one. It says, what happens if it's elliptical? You might be thinking, well, I can't solve it. It's not a uniform circular motion. You're right. You can't use uniform circular motion to figure it out. But you can use energy. You can use energy conservation. And so you just simply say that EG plus EK equals EG plus EK and solve it. And I think I got an answer of 3,394, something like that. Okay. All right. Okay. So thank you very much for sharing. And really quickly, let me kind of go back to the attendance thing then. So the attendance thing has to be done by midnight. That's SWIC. Again, it's pretty simple. Some people will be exempt, and I'll be able to tell you who you are here in a second, or some of you I'll be able to say. I won't be able to say everybody because I know some people at the right before the meeting sent me a bunch of whiteboards I didn't have time to look at. But for sure, I know these people are exempt. Let's see, Wendy, Sophia, Chloe, if you don't want to do this week, you don't have to, although it's not hard. So if you wanted to do it, and it's stuff that you know anyway, it'd probably take you 5 minutes. Gabe and Sydney, again, same thing. If you don't want to do it, you don't need to. I don't think it'd take very long if you wanted to. Jack and Nathan S. I think that you're exempt. You've done everything, so you don't need to worry about it if you don't want to. I think it's easy. And that's all that I know for sure. There might be other people. I can't tell you right now because I have to look at the whiteboards. Okay. So that's it. So thanks for coming. Oh, don't forget, then on Wednesday is the test. It's on Canvas. It has to be done by midnight. There's no meeting on Wednesday. That's it. Okay, see ya. Bye.